We present here a technique for time-frequency analysis of arbitrary signals, and then show what this technique gives when applied to sound. We start with a short discussion of the mathematics behind the technique, introducing the so-called wavelet transform, which is a modified form of Fourier analysis. Afterwards, we go on to describe the equipment used to record, analyze, and visualize the sounds, and finally give a set of examples where one can both hear and see the results. The procedure starts with a choice of a wavelet or elementary contribution into which the signal will be decomposed. What is a wavelet? You can see an example. The wavelet is a function that oscillates some, but then decays fast. If it did not decay fast, it would be a wave and not a wavelet, and we couldn't use it. If it did not oscillate at all, it would be a bump and not a wavelet, and again, with our techniques, we could not use it. More precisely, we require a wavelet to have, first, finite energy, secondly, to be smooth, and finally, to average out to zero. Since a wavelet averages out to zero, its Fourier transform vanishes for zero frequency. On the bottom, you see the positive part of the Fourier transform of the wavelet. The example here, incidentally, is the 8th derivative of a Gaussian. A wavelet has a certain average position in time and an average position in frequency. If we want to modify it in order to cover a whole range of positions and frequencies, we have to apply to it a certain set of operations which will be described in the next pictures. This slide recapitulates the conditions that are imposed on the wavelet. Conditions in time, conditions written out in terms of the Fourier transform. We shall now see how to modify the average position and the average frequency of the wavelet. In order to change the average position of the wavelet, you just move it around, shift it. For instance, from left to right. This is the displacement you see on the screen. In order to change the average frequency of the wavelet, you just stretch it or compress it. If you compress a wavelet, you dilate its Fourier transform, and so it carries higher frequencies. You can keep track of those operations with the help of a shift dilation plane, which appears now on the screen. You can see wavelets being shifted and the representative points moving around from left to right. Each time the wavelet gets dilated, the color of the representative point changes and the representative point moves upward. Each shift upward corresponds to the raising of the average frequency by an octave. you can see that the vertical scale of on the shift dilation plane is logarithmic. We'll now show the formulas which correspond to what you just saw on the screen. The dilation parameter is called A. It is a strictly positive number. Dilating a function by A means dividing its argument by A and dividing the result by square root of A. The shifting by B is the operation which you all know very well. And now finally we can see what happens if you first dilate and then shift. The resulting formula is shown now on the screen. And this is the wavelet associated to the point BA of the shift dilation plane. We should notice that shifts and dilations do not change the conditions that a wavelet has to satisfy. Now we can define the wavelet transform of a signal with respect to a wavelet. You can see a wavelet moving around in the shift dilation plane. At the top of the screen, you can also see a signal. It is a Heaviside function. The wavelet transform of the signal with respect to a wavelet is a function defined on the shift dilation plane. Its value at any point is, by definition, the scalar product of the shifted and dilated wavelet and of the signal. In the example on the screen, this value is given by the wiggles that you see below the red line. Later on, we shall introduce a more convenient representation for this function defined on the plane. Meanwhile, the most important thing that you should notice is that the wiggles of the higher lines are shorter than the wiggles that you see on the lines farther below. This means that the time resolution of our method improves at high compressions, which means at high frequencies. You can now see the formulas which define the wavelet transform of the signal S with respect to the wavelet G. The result is the function capital S of B and A. B is the shift parameter and A is the dilation parameter. In the integral, you see G bar. It is the complex conjugate of G. We have transformed the signal, which is a function of one variable, into a function of two variables. That would seem a dumb thing to do if one wants to store the result of the transformation. It turns out, however, that it is enough to store the result of the transformation on a certain discrete set of the shift dilation plane, which you can see here on the screen and which you will see in the next slide again. You see here that a dilated wavelet advances at a larger step than the compressed wavelet. This is very natural, intuitively, and it is also what the mathematics gives you. If you imagine this discrete grid continued to infinity in both directions, you can prove that a function is fully determined by the values of its wavelet transform of a grid of this kind. There is no loss of information when you go from a function to its wavelet transform. What you see now is one of many examples of reconstruction of a signal from its transform. The convergence is typically rather fast and does not involve many oscillations. You can now see formulas which allow you to reconstruct the signal S of t from its wavelet transform, capital S of BA. I would like just to make a few comments. First of all, there exist analogous formulas which involve only the value of capital S, the values of capital S at the points of a grid of the shift dilation plane. Secondly, the total energy of the signal can be obtained as an integral over the shift dilation plane of the square of the absolute value of the transform S of BA. An important question is the comparison of the windowed Fourier transform and the wavelet transform. The two methods have many features in common. The most important difference is the way in which one moves across a frequency range in the two methods. In the windowed Fourier transform, one moves across a frequency range by inscribing oscillations into a fixed envelope. In the case of wavelet transform, you move across a frequency range by compacting, contracting, or dilating a wavelet. This has an important influence on the convergence of the two methods. We'll now show the system used for sound analysis. Its central part is a CTER processor which is fast enough to handle sound in real time. It can perform 4 million operations per second. The complete system contains, in addition, 16-bit AD and DA converters that work at 32 kHz, a digital mass storage system, and a control part. The control part includes a PDP host processor, a graphic display, and a keyboard. The components are connected by a bus, which allows the host processor to send in real time information to CTER. In our case, this information includes sampled values of the analyzing wavelet. As of now, the system works as follows. First, the sound is numerized and stored. Then the wavelet transform is computed in real time for one value of the dilation parameter at a time. The result, that is the wavelet transform for a fixed value of the dilation parameter, is called a voice. We shall now describe the way CTER was programmed in order to calculate a voice of the wavelet transform. You can see the transverse filter used for the calculation. The discrete convolution involves 86 points in real time and can of course be extended if one accepts a lower sampling rate. This system can now be used interactively. The parameters of the transform can be input with the help of a mouse that moves around the settings. Now we modify the input level. Now we change the total number of voices. Here we give the number of voices per octave. And finally we specify the initial value of the dilation parameter. Let us now look at the results. We'll start with computer-generated signals and then go on to the analysis of real sounds. In this example, our signal is a pulse, a delta function, and so the transform gives the analyzing wavelet. We have here chosen an analyzing wavelet that has only positive frequencies. Consequently, as a function of time, this has a real and an imaginary part. What you see on the screen now is the real part of the analyzing wavelet, shown as a function on the shift dilation plane. Next, you will see the imaginary part. The real part was symmetric, the imaginary part is antisymmetric, as you can see. Since we are dealing with a complex valued function, it is natural to introduce the modulus and the phase of this function, which you see now on the screen. You see the modulus and the real part, and of course the modulus is an envelope of the real part. At the very top of the screen you still see the signal, which is a delta function. convenient to introduce color coding to describe the functions that we will see. And the next slide, which will be coming in a short moment, will be color coded. It will be the same picture as you see right now, color coded. You see again very well the narrowing of the features as you go up toward high frequencies. You see the signal again, but you see the palette starts from white to red. Sometimes we go into the next palette of colors. The picture that you see now is not anymore the modulus, but the phase of the analyzing wavelet. It's a beautiful picture. You see again the narrowing towards higher frequencies. It looks like a tower. You see that the time here is 16 milliseconds. And right now we change the signal. It will be still computer generated. It will be we will perform now a one voice analysis of a sinusoid that goes from 0 frequency to 16 kilohertz. We start with the dilation parameter A equal 1, and what we see now is the Fourier transform of the analyzing wavelet. We go now to A equal 0.25. Again, we see the Fourier transform. You see some small artifacts developing. The important part is that the Fourier transform has been shifted towards high frequencies, and it has broadened. The ratio delta f over f has remained constant. The next picture now is the analysis of a chirp, which goes from 1500 to 6000 hertz in 0.5 seconds. The analysis is done with 15 voices per octave, and it is centered between 2000 and 8000 hertzes. The total length of the image is 1.2 seconds. You see the very sharp transitions as the chirp goes down in frequency. You see that the picture is broader at the top, which corresponds to things we have already heard. You also see that the features are curved. This is due to the logarithmic scale that we use on the shift dilation plane. We see the same picture now in black and white. The intensity now is given by the density of black points. Since the transition of the between frequencies is so sharp, it is quite instructive to zoom in to a small time scale. Now you are at 16 milliseconds. The whole image corresponds to 16 milliseconds. Notice the very sharp transition. Notice also that the reconstruction of the signal, which you see on the top, with the help of reconstruction formulas, is extremely good. On the right-hand side of the picture, you can see the beginning of the rise in frequency. We will next see this same picture, but in phase. We are looking at the phase of the wavelet transform, not anymore at the modulus of the wave transform. You do notice that the upper left corner and the lower right corner show perfect coherence of phases. Those are the areas where there is something in the picture, and the areas where the modulus is very small show disturbed phase relationships. The sound that we analyze now is still synthetic, but much more complicated. It is a superposition of 8 periodic signals, each of which has many frequencies, many harmonics, and it shows beats. The sound has a global periodicity of 5.85 seconds. We analyze it here at 15 voices per octave for 3 octaves between 1000 and 8000 hertz, and the total length of the signal that you see on the screen now is 0.8 seconds. We'll zoom now to a smaller region of this same sound. We are zooming now to 16 milliseconds, where you see the regularity much apparent. You also see the very good quality of the reconstruction of the signal by the reconstruction formulas. We see now the same picture, but instead of looking at the modulus of the transform, we look at the phase of the transform. This will be our last synthetic sound, and we are moving on. As you see, we are moving on to speech signals. We start with a recording of pa, of the papi sound. It is recorded with 12 voices per octave. We are dealing with a range between 400 hertz and 8000 hertz. The length of this recording is 0.16 seconds, and you can see very well the formants of the pa. Since we are able to focus on very small intervals of time, we are going to go next to examine the explosive sound pa, p of pa. We are now at a time scale of 32 milliseconds. The screen corresponds to 32 milliseconds. You see the concentration of energy corresponding to the explosion. We change now sound and look at the ta of a ta-ti expression. Again, you can see the formants of the vowel. The time scale here is 0.16 seconds, and again we shall try to see the attack. We will move down in time scale. we see now the T, the attack of the T. The picture now covers 16 milliseconds. You do see again concentration of energy, and you will see now the same picture in black and white, again at 16 milliseconds. The signal now was S. It was recorded at 15 voices per octave, between 2000 and 8000 hertz. The total length is 0.38 seconds. Since we have cut off the low frequencies, the E sound is not visible on the screen, and only the S part is there. We look at the end of the S sound. The time now is 48 milliseconds, and now it is 16 milliseconds. Towards the end of this S sound, we think we see the trace of a noise that a bus outside of our window made when braking. The level of this noise is much lower than the sound that we recorded. We now go on to a sound of a true motor, which will come in the next slide. We analyze the sound of an electric motor. Here you see the onset of the sound. We are recording between 795 and 8000 hertz. The time scale at the first thing is 0.16 seconds. We will next go down very much in the time scale. We are now at 16 milliseconds, and we are looking at a stationary sound. The motor is not accelerating or decelerating. You see locally quite strong peaks in the sound. We look now at the acceleration of the motor over 0.32 seconds. You see the rise in frequency, and you also see the increase in energy. Both those features can be seen on the signal and on the transform. We are still looking at the modulus of the transform. We would like to end now with some more pleasant sound. You have heard the clarinet, and you have noticed that it does not sound like an electric motor. You can see also that its picture does not look like the picture of an electric motor. You have here an analysis at 15 voices per octave, between 795 and 8000 hertz. The time scale is 48 milliseconds per screen. You see the attack is very sharp. There is lots of energy in a given frequency range. We will be zooming now to a 16 millisecond scale. You can see the almost perfect reconstruction of the signal by our analysis, by looking at the graph above the thing. You still see very sharp concentration, very sharp onset, arrival of energy. We go now to a much larger time scale. This is a picture of 3 notes of the clarinet, A, B and C. The time scale here is 0.96 seconds.